Okay, good morning. Uh, so, we have been discussing about various ways of designing binary digital counters. Yesterday, in the last topic, I believe it was done very hurriedly, so I wish to start from there. Till now, I think the lockout, why it occurs and how it can be prevented, that is clear to all of you, is it not? However, if the question asks you to prevent the lockout, then only you go ahead with this. If not, that means the question does not ask you to prevent lockout. You can say, if you are asked to design a modulo 6 counter or modulo 7 counter or modulo 5 counter, if lockout prevention is not asked for, please select any k when you are asked to design a modulo k counter. Select any k out of the 2 to the power n possible by choosing for n minimum number of flip-flops and leaving out 2 to the power n minus k states and go ahead with the design. However, if lockout is specifically asked for, then only go for prevention of lockout, because that will increase the design exercise. Okay. And next we have been discussing about the combination of modulo counters. Yeah. So here what we saw is that if you place in cascade a modulo m counter and a modulo k counter, then the total configuration will give us a modulus or base of m multiplied by k. Okay, so for example, a modulo 2 counters placed in front of a modulo 5 counter will give me a modulo 10 counter when you are considering the states of all the 4 flip-flops together. However, you have to know that what is the code of the, what are the states that the circuit, the sequential circuit will go through. That will depend on the configuration of the counter. So that means this is a modulo 5 counter which we are showing in the dotted rectangle, and this is a modulo 2 counter. Any flip-flop by itself will behave like a modulo 2 counter. However, if you permute their position, that means place the modulo 5 counter first, followed by modulo 2 counter, and feed the system clock to modulo 5 counter, then this code will definitely not remain the same. Okay, that you have to understand, right? So what will be the code like, that you have to clearly work out. Okay, because this modulo 5 counter you have worked earlier, so you know what are the states, and modulo 2 counter you know. So if you place them first, followed by these, so what is the total, what are the total individual states, that you have to work out by starting with a given initial state that is permissible, and then proceeding ahead till that particular initial state returns. So you know how to work out the sequence of states for any counter, be it sequential or be it synchronous or asynchronous. Clear? I believe it is clear to all of you. If any doubt, please ask me. Next, what I have been doing is the idea of decoding logic. Why is it necessary? That is the question. See, the decoding of the states of a counter, when it becomes necessary, is that if you think of computer architecture, typically the processing unit consists of, say, ALU and shifter. Okay, in some case multiplier may be there also, and there will be a controller. So controller, what it does, it decodes each individual instruction and accordingly issues control signals so that the data processing unit, the arithmetic unit, can do data processing operations. Okay, and it can also involve the presence of registers where the intermediate values are stored. Then, if you have for the controller, if you have a hardware control unit, you can have hardware control unit or microprogram unit. So for hardware control unit, definitely there will be a counter at the heart of the controller. That counter will, when it goes from state to state, some or other actions will be performed, like obtaining data from a specified memory and issuing out control signals, like either, say, storage of intermediate data to a particular register, or say to a particular tertiary memory or secondary memory. Also, in case of general industrial system, when a controller is passing through a particular state, Okay, at a particular state, maybe a motor can be made on or a furnace can be made on. Okay, like that. Okay, so different operations take place at distinct states of the controller, and always there is a counter at the heart of the controller. So we need to decode each of the states of the counter, at what state the counter is resident now, and accordingly we'll issue out the control signals. So decoding of the states is very important. Based on that, we can issue out different control signals. Now here the modulo 10 counter or decode counter has got or a decade counter, I'm sorry, decade, DECADE, a decade counter or a modulo 10 counter has got 10 distinct states. For this particular 4-bit counter, these are the states, and each of the 10 states, okay, can be decoded uniquely. So how to decode that? That means each of the decoding logic is nothing but a function of 4 Boolean variables. What are the 4 Boolean variables? Those are the states of the 4 flip-flops. Okay. So in order to decode the states of the counter, what we do? We draw a 4 variable Carnot map. So where Q0, Q1, Q2, Q3 are the principal variables for the K map, the 4 variable K map. And suppose we want to, and also we need to know that out of the 2 to the power 4 or 16 combinations, only 10 are used. So 6 are unused. Those unused states we can put don't care or X in the proper boxes, right, in the cells. Then it helps us to optimize the decoding logic for some of the states. Mind you, not all the states. For example, these 10 states will be there mutually exclusive in time. That means when this particular state is active, all the other 9 remaining states are inactive. So in the boxes, suppose we want to decode the logic for state 0, okay, which is given by all the flip-flops in the clear state. Then only this particular box we have to put 1, and the remaining 9 boxes we have to put 0. But in addition, these 6 don't cares will maybe of help to us. However, if we write a 1 here at the left top corner, it can be only combined with this, okay, or this, sorry, this and this. However, these 2 are zeros, this is 0, this 8 is also 0 because it's state. So 0 cannot be combined with anybody, and hence we have to employ a 4 input AND gate for decoding this particular state. Similarly for 1. However, if you look at the state 2, 2 can be combined with this state 1, 0, which is a don't care state. So 2 and X will allow us to eliminate a single variable. Okay. And the best optimization will be possible for state 8 and state 9, as we see here. For state 8, you see, okay, so this will be 1, this will be 0, the other 8 will be 0. However, with the help of these don't cares, we can combine these 2 and these 2. So in effect, combining the 4 cells, we get the decoding logic for state 8 to be Q3 and it with Q0 bar. So you can work with the 2 input AND gates, right? Similarly, for state 9, 1001, this will be 1, this will be 0. So we can combine the surrounding neighbors with 9, and hence it leads to the decoding logic leads to a 2 variable AND function. So somewhat simplified. Okay. So this is the idea of decoding logic, how we can generate the decoding logic for individual states. Later on, I mean today also, as we progress in our class, we'll make use of decoding logic. Okay, clear so far? If any doubt, you let me know. And
So for
one,
the K-map, sir, instead of
yeah, yes, yeah.
sir, instead of taking 2 quads, we could have directly taken 1 8 block, like 8 terms common together.
Now in this particular example, it is not possible. Why? Because you see that there are 10 valid states, okay, 10 legal states which will occur in the time sequence, and at any point of the time, one and only one will be asserted. Okay, so when only one is asserted, say for example, look at 5. when 5 is asserted and its nearest neighbors are 4, 1, 7, 13. So 4, 1, 7 will definitely be 0. Okay, when 5 we are putting a 1. However, 13 happens to be a don't care state and we can combine 5 and 13. If you do so, you see that the variable Q3 gets eliminated. Okay, so by combining 5 and 13, what we get? I see that we get it Q1 bar, Q0 and Q2. Okay, so Q2, Q1 bar, Q0, right? So here at best you can combine 4 boxes, not 8 boxes. Okay, so 8 and 9, if 8 is active, 9 will definitely be 0.
Yeah,
Okay.
sir. Understood. Sorry, I was
Okay.
wrong. Yeah.
Okay. Thank you. Thank you for pointing this out. Okay. Right. So, however, if we tend to decode a modulo, a modulo 12 counter, modulo 17 counter, modulo 18 counter, where we record say at least 5 flip-flop, then it may be we may be lucky to get a 8 cell combination. Okay. Instead of quad, we can still get a octet. Thank you for pointing out the question. Now, let us now take up the design of a non-binary counter, but sticking to the ripple counter design. Now, you can question why we are studying this. The reason is that it is very simple to arrive at configuration of a ripple counter or asynchronous counter directly by connecting the flip-flop output to the clock input of a particular, that means flip-flop output from the immediately left neighbor to the clock input of the flip-flop. Okay, like that. So although there will be some delay, but we'll get all the states possible for this 2 to the power n counter. So here n equal to 4. Now modulo 16 counter, modulo 8 counter, whichever, I mean, wherever the modulo or the base is a power of 2, it is very simple to arrive at just by fixing up the flip-flops with proper interconnection. The leftmost flip-flop you drive with the primary clock, okay, and henceforth, I mean, after that, just connect the uh, normal flip-flop output to the clock input of the next immediately right neighbor. Okay, and you will definitely get modulo to the power n counter. But suppose and also we have so far seen that if it is a non-binary counter, that means the modulus is not a power of 2, then also we can do, but provided that we have to have a specified state sequence. Okay, and based on that we can design by using JK flip-flop. Okay, so that is also possible. Now, now the question is that can we simply we stick to the ripple counter design, because it's very simple, and just make slightly modify that so that we can get a non-binary counter. Of course, the modulus should be less than the modulus of the ripple counter that we can generate. So here, for example, it will give me a modulus 16 counter at most. So now suppose we have to generate a modulo 15 or modulo 14, modulo 13, modulo 12, modulo 11, modulo 10, we can definitely make use of that. The same configuration, but what you have to make use of, in addition to the normal flip-flop output, we can make use of asynchronous flip-flop inputs, namely direct set or direct reset inputs, say preset and clear. I mean, those preset and clear input, I am sure all of you are well familiar with, because you are using this in your online lab class. So in fact, you have seen 7474, which accommodates two number of positively edge triggered D flip-flops. It has got its preset input and clear input. Okay. Similarly, 7476, although you have not used maybe, but it provides two JK flip-flops with active uh, what you call 1 to 0 transition triggered flip-flop. That also has got a preset input and a clear input. Okay, and that preset input and clear input overrides the data input and the clock input. So when it is, you are setting it to on, making it active. Okay, so then it will make all the flip-flops to be the flip-flop to be set or reset like that. So preset and clear should not be made on simultaneously. They should be made, they should be activated at mutually exclusive time. Okay, so here what we do, we are explicitly showing the direct set input, because with that only we are working. in this particular scheme. So here we show an alternative scheme of designing non-binary counter. So what we do, we allow ripple counting throughout and yet permit an arbitrary modulo. What we do, use the asynchronous flip-flop inputs, namely the direct set. Here we choose to design a modulo 10 or a decade counter. So what we require an external gate, here a 3 input NAND gate. And why it is an AND gate, why the fan-in is 3, that we are now going to discuss. Okay, so interconnection between the successive flip-flops are purely toggle connection, ripple connection. So the clock input of FF1 is driven by the Q0 output, the normal output of FF0. The clock input of FF2 is driven by the normal output of FF1. Now, the clock input of the FF3 is directly driven by its immediate left neighbor, namely Q2. Okay, you can expand it, you can expand the scheme, okay, without any bound. So interconnections between the successive flip-flops are toggle connection. Assume that the direct or asynchronous set inputs are active low. That's why we written S bar. Starting with the initial state, okay, if you look at the fact, okay, that what you have put a 3 input NAND gate whose output is symbolized as Y, capital Y. And that is connected to the set input of FF1 and FF2. Now, why is it so? If you start, so for your benefit, I have read the state of the counter. So assuming that all the flip-flops are negative edge triggered, so the triggering transitions we have numbered as 1, 2, 3 and so on. Here you see that although it could have gone up to 16, but we have numbered it in this manner, 9, then 10. And stop. After that, this 000 state is returning. So that means it will definitely work like a modulo 10 counter. But how? Without proceeding to 10, 11, 12, 13, 14, 15, it skips all the 6 states, and from 9 it directly comes to 0. Why is it so? So as we can see here, the direct asynchronous state inputs are active low, starting with the initial state Q0 equal to Q1 equal to Q2 equal to Q3 equal to 0. And through the count of 9, that means still the count 9 appears here. 1, 0, 0, 0, all the 9 states have appeared. After that, what happened? You see here at this trailing edge, okay, that 1 to 0 transition, we have numbered it as 9, but at this point, you see state 1001 is reached. Okay, so right, because all are negative edge triggered. Although not simultaneously Q0, Q1, Q2, Q3 will be made on, will take what you call, will have transition. But if you neglect, if you ignore the delay through the flip-flop, as soon as the active edge trigger takes place in the clock, definitely what will happen, you know, FF0 will have a transition from 0 to 1. Okay, and also FF3, not FF3, okay, only FF0 will have a transition. The remaining Q0, Q1, yeah, Q1, Q2 will remain same, Q3 will also remain. So after 1000, it will become 1001. Clear? Now, next, rising transition of the clock. Please, all of you, if you pay attention here, what happens? Here, this one. So at this point, what happens? The operation is precisely at the middle, as over the counting range, y equal to 1. Y will remain 1. That also I have shown. So if y remains 1, what will happen? It cannot affect the set input because these are active low. Okay. And y is high till then because Q0 and Q3 are connected. So Q0 and Q3 are not yet both 1. It has become 1 only here. From this point onwards, the Q0 and Q3 has become 1. But the clock is not 1 because this is the off time of the clock. Okay, so third input clock is 1. So, sorry, clock is 0. So hence the output is 1. It will become 1 only after the rising transition of the clock. So here you see Q0 is 1. So all of you, if you put attention on this vertical line, you see Q0 is 1, clock is 1, and Q3 is 1. So all the 3 inputs of the NAND gate, Y, whose output are denoted as Y. So this 3 input NAND gate it will have its output to be, as all the inputs are 1, what will be the output? Q0 is 1, Q3 is 1, clock is also input, clock is also 1. Okay, that means we are focusing on this point, right? So, as you can see, what will be the output? Anyone? Dear friend? Q0 is 1, Q3 is 1, and clock is 1. At this point, if you focus.
It
Okay,
would be 0.
exactly, very good. Okay, so all the inputs being 1, the output will be 0, and this 0 is fed to the asynchronous set inputs of FF1 and FF2. So this set input, we understand, it will override the operation of the clock input and the excitation input. So it will force the FF1 and FF2 output to go to 1. Okay, so hence I have written for you is that as soon as the rising edge will occur here, the clock, that means the clock has become 1. Okay, so this is a mere NAND gate and it can override. So no delay of the flip flop will be involved here. Based on the delay of the input NAND gate, as soon as the signal has passed from the input to the output of the NAND gate, then this will be present here, and it will also within the flip flop also some NAND gate or AND gate is there. So the output will go to 1. Q1 and Q2 will be going to 1. So we see that after the for the 10th clock pulse, if the clock has become 1, after that immediately FF1 and FF2 output will become 1. So that means now at the present instant, FF0, FF1, FF2, all four flip-flop outputs will be at logic 1. Clear? So that means effectively what we have done, we could skip. I mean, just 1010. Sorry, after 1001, 1001 was attained. After that, the next 6 states, okay, next 5 states, namely 10, 11, 12, 13, 14. These 5 states are skipped. Immediately we come to all 1. Clear? So at the positive going clock transition, after the 9 flip-flop triggering transition, all the 3 inputs of the NAND gate are 1, and so y equal to 0. So FF1 and FF2 will go to set state. That means they will become high. And now Q0 equal to Q1 equal to Q3 equal to 1, which is a state for the count 15 equal to 1111. So count is advanced from 1001 equal to 9 to 1111 at one step immediately. That means by skipping the 5 states, namely 1010 corresponding to 10, then 11, 12, 13, 14, right? So all the 5 states are just bypassed, and we immediately arrive at all the 1 state. Okay. So now what is the situation? When the next active edge will come, that means the next 120 transition will come, it will behave like the last state of the modulo 16 ripple counter. So all the flip-flop outputs being 1, first Q0 will have a toggle, will have transition from 1 to 0. That will cause a toggle here, 1 to 0. That will cause a toggle here, 1 to 0, and then, right? Okay. And you can question, you have got a 3-input NAND gate whose output is connected to the set input. So what will happen? Yeah, let me answer that question also. So here you see y will immediately become 1 with the arrival of the 1 to 0 transition of the 10th clock pulse. That you have to keep in mind. Okay, as soon as clock gets to the logic 0 level, okay, it will set the output of y to low. I'm sorry, it will set the output of y to high, because clock has become 0 here, and that will no longer affect the direct set input of FF1 and FF2. Clear? So then it will be normal clock induced operation. That means when a clock is happening here 1 to 0, it will lead to a change in Q1. Q1 was earlier 1, now it will become 0, and this toggle will affect next FF2, because S bar is no longer affected by the output of the 3-input NAND gate, right? So Q2 will normally have a transition from 1 to 0 as J and K are connected in toggle mode and the clock has undergone a 1 to 0 transition. In response, Q2 will go to 0. And finally, as Q2 has a transition from 1 to 0 and it is fed as clock input of FF3 and its J and K inputs are connected to high. So then Q3 also finally come down to low. That means all the flip-flop will have a reset state transition. Is it clear? That means when clock next goes to 1 to 0, A ripple is started through the cascade. Why do we say a ripple? Because first FF0 will have a transition in response to the clock. See, for FF0, it is faithfully dividing the clock frequency by a factor of 2. So whenever there is a 1 to 0 transition in the clock, J and K are connected to 1 and the set is connected to 1, that is ineffective. So Q0 will always have a transition from 0 to 1 or 1 to 0 depending, because it is in toggle mode. Okay, so FF0 will work unhindered. So here also it will have a transition from 1 to 0. As a result, Q1 will have a transition and so on. Now, if some doubt persists in your mind, please let me know that you may be wondering there is a chillput NAND gate whose output Y is affecting the direct set input of FF1, FF2. So will it come in the way of normal operation of FF1, FF2? To answer that, let me tell you, as soon as the clock as it transitions from 1 to 0, immediately Y will become high and its effect will be earlier than the effect of FF0. Okay, so clock falling from 1 to 0, that will affect FF0, that will affect the NAND gate. But NAND gate only a single gate. So compared to the delay through the FF0, remember if the JK flip-flop is a master slave flip-flop, it will pass through no less than 4 number of gates. Whereas here the signal is passing through this only one NAND gate, and after that maybe it is directly connected to the final NAND gate. So it will, here the signal propagation is through 2 gates, whereas here the signal propagation is through 4 gates, right? So definitely the set input, its effect will be annulled. The influence of the S bar, the direct or asynchronous set input, will be nullified prior to the transition in FF0. So only after the effect of the set input becoming ineffective, the FF0 will have a transition from 1 to 0. And again, and still after that, FF1 will have its transition. So, I mean, no problem in FF1 and FF2 to operate as per the command issuing the clock input of FF1 and FF2. Clear? Any doubt still you can ask me. Okay, I'll try to answer. So
Sir,
now, yes, please. Yeah.
Sir, in the 10th input, all the flip-flop outputs are 1.
Yeah.
Sir,
Exactly.
but in that case, if the decoding logic doesn't know which state means what to operate at all, wouldn't that cause certain problems in controlling the system which we have?
Excellent. Yeah, very good question. Now, so that means, of course, a decoding logic should be there here also. Now, the decoding logic, in order that a decoding mechanism is activated, for that normally we have a strobing signal. So some strobe signal is there. For the other states, it is not much of a problem. So we can send the strobe signal at the rising edge of the clock. We can that means we can synchronize the reading of the step with the rising edge of the clock. So more or less it will act fine. But what will happen here? What will happen here is that depending on the on time of the clock, so normally if you have to read the all one state, so we have to wait for, you see, we have to wait for what? That means it is only in connection with this 3-input NAND gate. So 3-input NAND gate means when the clock happens to be 1 here. Okay. So what is the sequence of event that, let me tell you. First, the clock will go from 0 to 1. Then the output of the input NAND gate will be generated, and then it will affect the further 2 NAND gates. So 2 input NAND gate delay will be involved. That means when the strobe signal to read out the state of all one is necessary to be generated here. Now you have to we have to add some more delay. Okay, so that delay is nothing but adding the delay of 2 NAND gates in succession. And definitely we have to take care in designing the clock on time. That means the clock on time. Now again, as you are designing the sequential circuit, the length of the on time, length of the off time, length of the period of the clock will be of utmost importance. Now that you have raised a very nice question, very pertinent question. So it actually facilitates the discussion. The on-time duration of the clock, that should be at least greater than, that should be actually for safety, that is kept uh, larger than the sum total of two NAND gate delays. Okay. So if the NAND gate delay is say 5 nanoseconds, for the only for the sake of discussion I'm telling, normally it can be as low as 2 nanoseconds or maybe much less. So suppose 5 nanosecond delay is encountered for each NAND gate, typically 3 input, 2 input, 4 input, that will vary slightly. If you take the typical delay to be 5 nanoseconds, then assuming that the signal will travel through this NAND gate followed by another NAND gate at the output of the flip-flop, so 2 NAND gate delay means 10 nanoseconds. So the on time of the clock should be larger than 10 nanoseconds. So we can make it 20, 50, 30 something, somewhat, okay. Right? So decoding of the states of the counter is of utmost importance, as we have noted earlier. So here also it may be necessary to read the all one state. For that, the strobing input, that means the decoding logic, has to be enabled after the rising edge of the clock. Okay, some delay will be there, and that can, you can question how the delay will be worked out. Yeah, for working out the delay, normally we take into account some monostable flip-flop, monostable multivibrator. So that means after the event rising edge has taken place, then through RC circuit we can generate a delay of say taking into account 10 nanosecond delay for two successive NAND gates. We can generate a delay of 20 nanosecond. After that you generate the strobing pulse, strobing input. Okay, so now we can read the state of the counter and it will be definitely showing all one. Okay, so that's how it is. Just one suggestion I am giving. You may have some more efficient suggestion when you I mean from actual in the industrial house how it is done. So this is a very pertinent question you asked. You have to read the state of the counter. For the remaining states, it is not a much problem, because as soon as the rising edge is coming, we can read the state, because at the rising edge there will not be any alteration in the output of the flip flop. Okay, but however here, as the flip flop, the influence of direct or asynchronous inputs like set input, so we have to be extra careful in order to read the state of the counter. So what we can do, after the rising edge occurs, let us wait for a sum of propagation delays to the two NAND gates and then read the state of the counter. Okay, is it clear?
Yes,
Okay.
sir.
Thank you.
Sir,
So yes.
Sir, in the clock signal which we're sending is kind of asymmetrical clock, right? Means its duty cycle is less than 50%. But whatever output we generate to Q0, Q1, Q2, and Q3, they are kind of symmetrical, right? With duty cycle of 50%, right?
Oh, yeah. The flip-flop outputs are having 50% duty. That is there. But the
Yes,
clock
sir.
input is normally asymmetrical.
Yes, sir. So if I want my flip-flop to be Fs by 2, means the Q0 output should be Fs by 2, but it should kind of follow my clock signal. Means it should be symmetrical with duty cycle equal to the clock pulse. Then is it possible then?
Oh, that means you want to make the output of the flip-flops to be asymmetrical. Yeah, that is your question.
Yes, sir.
Here, for example, for Q2 and Q3, we can see that it is automatically asymmetrical. Yeah, here, yeah, for actually Q0 will always be symmetrical, 50% duty cycle. Here, however, it is not possible. Okay, so but that will not cause any problem. Only thing is that you have to read the state of the counter. So the event should be of more importance rather than taking into account the length of the on time and off time. So event means the rising appearance of the rising edge. After that, you can give some delay and you can set the reading time. Okay. So I think the it is actually event triggered rather than what you call the reading operation. The reading procedure should be event triggered, and that is the appearance at what you call the arrival of a 0 to 1 transition in the clock. Okay. After that, you wait for sufficient amount of time, then you read the state of the counter. But so far as I can see, there is no what you call critical need to keep the duty cycle of the periodic waveform which is available at the Q0, Q1, Q2, and Q3 to be in consonance, to be in agreement with that of the clock. It can be independent. I mean, so far as I can understand. Okay. Now, so in general, we have designed
Sir,
a mod.
one thing.
Yeah. Please. Yeah. Exactly. Please.
Is there any specific reason for keeping the clock signal asymmetric?
Well, reason. Actually, let me tell you one. If you can sorry, if you can allow me to make a what you call unbiased statement, there is no need to keep the clock signal even periodic also. I mean, forget about the asymmetry. The clock signal can even be made to be say aperiodic. Okay, so only thing is that the 0 to 1 transition and 1 to 8 transition should be clearly defined. There we should not provide much jagged edge or what you call some jitter, something like that. So when the 0 to 1 transition is occurring, as far as possible, this transition should be available for a synchronous counter at the same point of the time to all the flip-flops. Okay. Apart from that, I don't think there is much what you call restriction on the duration of the or on the necessity of the clock to have what you call asymmetric duty cycle. Okay, it can be anything, symmetric or asymmetric, but only thing is that the 0 to 1 transition, 1 to 0 transition should be clearly defined because it will affect the flip-flop what you call generation of the output. So there you should not provide much jagged edge or what you call some jitter in the arrival of the clock at different points of time. So as far as possible, that's why the clock buffer, the design of clock buffer also assumes importance. Okay, because the delay, if you have a 6-bit counter, let us say, so we have to ensure that for synchronous counter, it is necessary that the clock should be available at all the clock inputs of all the flip-flops. So if you increase the number of flip-flops without bound, that can be a bit difficult. Okay, because there will be slight relative delay between the arrival of the clock at different flip-flops. So that's why you may say, as we have seen, partly synchronous, partly ripple design also are acceptable, because that will reduce to some extent the loading on the clock driver. Okay, if you design a 12-bit counter, 16-bit counter, fully synchronous, then the clock the clock signal will have to feed not only no less than 16 number of flip-flops, and that can lead to a strain on the loading ability of the clock driver, right? So we can always augment your design based on the need. Okay, there is no doubt about that. But so far as possible, as I can see, there is not much critical need in having to keep the clock with a particular specified duty cycle. I mean, that is as far my knowledge goes. Probably for some meet the need of a particular design, particular situation, it may be required. Okay, but for the time being, I can see that only 0 to 1 transition and 1 to 0 transition should be clearly defined, and it should be fed to the flip-flop input. Not much need or requirement of keeping clock signal with a particular duty cycle. Okay, so far as I know. If I come to have any more knowledge, I'll definitely share with you. So general steps to design and realize a modulo K counter where K is not a power of 2. What is that? You choose n flip-flops such that this inequality is satisfied. So suppose modulo 17, then n should be 5. If I have K equal to say 33 or 35, I'll have n equal to 6, something like that. So we choose the n flip-flops and just plain and simple make the ripple connection. Okay, do the design. And then choose a NAND gate. The fanning of the NAND gate will, however, be irregular. That means we cannot predict it. Depending on our need, we have to take it. NAND gate has as inputs the clock input and the Q output of each flip-flop, which is in the set state at the count K minus 1. Okay, so here, for example, K equal to 10. So at the count 9, whichever flip-flops are in the set state, namely Q0 and Q3. Okay, so Q0 and Q3 will be at set state when the count 9, namely 1, 0, 0, 1 will be appearing. So those flip-flop output should be connected as inputs to an AND gate. Okay, and in addition the clock input. Okay, so NAND gate has as input the clock input and the Q output of each flip-flop, which is in the set state. Okay, Q equal to 1 at the count, at the what you call pre-terminal count, okay, pre-final count K minus 1, right? And the output where I am feeding it, the NAND gate output is connected to the direct set inputs of each flip-flop, which is in the reset or clear state, Q equal to 0 at that particular penultimate count, K minus 1. So here in 1001, FF1 and FF2 will have their output to be 0. So you feed the output of the NAND gate to the set input of those two flip-flops only. Okay, so this is very simple design. Now, once again, we take up the synchronous counter design. Still any doubt you can ask me. So here what we do, we take up a, sorry, not synchronous counter, ripple counter, but now we allow the counter, the counting sequence to proceed in forward direction as well as backward direction. Now, what do you mean by forward and backward? It is as simple as that. So if we read the count as per this equation, say K is the count value, decimal value. So we have a 4-bit counter where rightmost flip-flop takes the most significant bit of the counting state. Leftmost flip-flop has the least significant bit of the counting state. So K we are writing to the power 3. That means we are reading the count in 8421 sequence. So 2 to the power 3 Q3 plus 2 square into Q2 plus Q1. And so this is the equation. Then the modulo 16 ripple counter will count in the sequence with the progression of time. So 0, 1, that means all of the flip-flops are in clear state, and finally it will attain the state all set state. Again, the next state will be all reset. So that's what you have seen for the ripple connection. Now that will happen, as you can see, that when the connection, that means the clock input of each flip-flop is directly fed by the normal output of the immediate left neighbor, right? That is clear. But suppose I want the counter to proceed in the reverse sequence. That means, say here 15 followed by 14 followed by 13. Like that, it will come down to 0, and after the 0, it will go to 15. Okay, right? So this is 0 is the saturation. After that, it will go to 15. So that it will revert to the all set state. The counter then will be it will be named as a down counter or a backward counter. For that, you see, you have to connect the complementary output of the immediate left neighbor. Now, why is it so? Let me just answer it. Suppose we start with all 0. All 0 means here 4 flip-flops, all of them are in reset state, clear state. Then if the normal outputs are 1, the complementary output will be, sorry, what did I say? Yeah, all 0 means normal outputs will be all 0. That means Q3 equal to Q2 equal to Q1 equal to Q0, all are 0. That means the complementary output will be in the set state, namely Q3 bar equal to Q2 bar equal to Q1 bar equal to Q0 bar equal to 1. Okay. Now suppose Q0 bar is connected to C1. Okay. Next, what will happen? So with all 0 being the present state, what will be the next state? That we want to find out. So next, what will happen? There is a pure and simple ripple connection. Now when clock will give 1 to 0 transition, FF0 will have a transition, so it will go from 0 to 1. Okay, earlier it was 0. Now this 0 to 1 means a 1 to 0, the reverse transition will be present here, and that will be fed to the FF1, which is triggered by a 1 to 0 transition. So that means it will also change state. So from earlier it was 0, now it will go to 1. As it goes from 0 to 1, the reverse transition, namely 1 to 0 will be fed, and that will be connected here. And so it is in toggle mode also. So Q2 will have a transition, it will go from 0 to 1. That means Q2 bar will go to 1 to 0, and that is fed as a clock. So FF3 will also have a transition from 0 to 1. That means 0, if the present state is 0, I am writing the decimal equivalent. That means if Q3, Q2, Q1, Q0 all are set reset, that means 0, then in the next state it will become all the flip-flop output will be in set state. So from 0 it will go to 15. After that, you can verify that only this fellow will be having a transition, not the other ones. Okay. Why also you can tell me that if now it will have a transition, so it will go from 0 to 1. Sorry, 15 means what? it will go from 1 to 0, but 1 to 0 it will have 0 to 1. Now that is a rising transition. Rising transition cannot affect a flip-flop with the negative edge trigger transition, right? So FF1 will remain unchanged, FF2 remain unchanged, FF2. So that means from 1111 it will go to 1110. So it will proceed in a downward direction. After that 13 will come, after that 12 will come, right? After that 0 and finally 50. So it will also have 16 states. Remember that the same states will be there in both the counter, but in the reverse direction. I mean, you will not have a state which exists in this forward counter but not in the backward counter. No, you cannot design a counter like that, right? So that means the states that exist for the forward counter will definitely exist in the backward counter as well. There cannot be a state which belongs to up counter, not to a down counter, because you have the physically the same circuit template, right? So it is like a FSM, finite state machine. Finite state machine means what? It will pass through 16 states. Okay, no more than 16 states, no less than 16 states, and it will have a cycle of 16 value. So starting with any initial state, it will pass through next 15 states and then get back to the initial state. That means it will have a cycle of value 16, like a graph. Okay, starting from a node, you traverse the remaining 15 nodes and get back to the initial node, initial vertex, right? So depending, acha, in order to, that means how you are designing. Basically, you have got, say, you have to visualize that as if you have designed two different counters. But in the spaces between two successive flip-flops, you have put some multiplexing arrangement. Some external gates you have put. Depending on the logic of the there is a control signal you put like up and its inversion. That means we name it as down and up bar basically. So it is a 2 to 1 multiplexer. Okay, up is the control signal, Q0 and Q0 bar. These are the two data inputs, and the output of the 2 to 1 multiplexer is fed to the clock input of the immediate right neighbor. You get it? So just by putting this 2 to 1 multiplexer in between each consecutive pair of flip-flops, we can attain a up-down ripple counter, up-down asynchronous counter, mind you. Depending on the value of the control signal up, if up is at logic 1, then this entire counter will be working as per the forward direction. On the other hand, if up is low, down is high, so it will act like a downward counter or a backward counter, down counter or back counter. Now, if you think of a up-down counter, but modulo 3, which is a non-binary counter, synchronous, right? Here it is ripple, mind you, but if you think of a modulo k counter, where k is not a power of 2, then you have to design the counter properly. That means design for its forward version as well as for reverse version. Connect the two via again some multiplexing arrangement. So modulo 3 is very simple. Suppose you decide to have 0, 0, 0, 1, 1, 0 in your prescribed state assignment table. So the same state will be there but in the reverse direction. So here if this is a present state 0, 0, next it will be 0, 1, 1, 0 and next 0, 0 returns. Here however you start with say 0, 0, then you go to 1, 0. That's what I have written here. If present state is 0, 0, next it will be 1, 0, next it will be 0, 1, next again 0. So it will return. And the modulus of both the counters are 3. Okay. So for this is the for the down counting, this is for the up counting. And we require two flip-flops, okay, whose excitation inputs are J1, K1, J0, K0. These are more significant flip-flop, these are less significant flip-flop. So J0 and G1, K0, K1 are designed by filling up the excitation columns. You can easily design it. I have not written it. On the other hand, you see here it is required that J0 should be Q1, but here it is Q1. So just a choice between the complementary output and the normal output of the right neighbor. And here also simply normal output and complementary output of the immediate left neighbor. And K0 are always 1. So it is very simple. K0, K1 you can connect it right to logic 1. J0, J1 you have to feed via a 2 to 1 multiplexer. Okay, so that means as simple as that. So J0 and J1 will be driven by a 2 to 1 multiplexer. Okay, whereas before if you have a up signal working as the control input of the 2 to 1 multiplexer. So up determines whether the counting will proceed in the forward direction or the negative, the what do you call, backward direction. Okay, so up is 1, it means that we want the counter to go forward direction. That means starting with 0, 0, 0, 1, 1, 0, and then revert to 0. On the other hand, if up is low, we want the counter to proceed in the backward direction. That means start with 0, 0, then following state will be 1, 0, then 0, 1, and again 0, 0 returns. Right? And how we can do is very simple. So feed the system-wide clock to the clock input of all the flip-flops, and then interpose a 2 to 1 multiplexer before each excitation input of the flip-flop. Right? So what we are doing basically, as if we are designing two separate counters, the up counter is designed to step through a sequence of counter states in some specified manner. The down counter is then designed to step through the same sequence in the reverse counter. And external steering gates are added to change the connections from those suitable for one direction of counting to those suitable for the other direction. Right? So very simple. Acha. So you can then design, I've done only up-down modulo 3, you can design for up-down modulo 5, up-down modulo 7, and so on. So you know the design principle. Okay. You design for both. Okay, so J0, J1. So that means J0 will be this for forwardation, J0 will be something else for the backwardation. Just put a 2 to 1 multiplexer and drive J0. Now, if it so happens that, say, apart from J0, J1, K0, K1 also will be something else, then you require a 2 to 1 multiplexer for K0 and K1. That's true. Multiplexer is like steering. So choose one input or the other, depending on whether you want to proceed in forward direction or backward direction. Is it clear? Any doubt? That means we are going for programmable up-down counter. Yes, yes. Please.
So instead of using two AND gates and an OR gate, can't we use a single XNOR gate with up and Q0 or Q1?
Okay. Two AND gate and one OR gate. Sorry, two AND gate and one or two AND gate, one OR gate. You want to use the XNOR gate equivalence. But what will be the input of the XNOR gate? It's the equivalence gate. What will you
like for the after the first flip flop, it would be Q0 and up for the XNOR gate.
Is next. What the XNOR gate? Okay, so okay, up and Q0 plus Q. Yes, yes, exactly. Thank you, thank you. Very good, very good. Yes, you're right. Absolutely right. Yes, yes. Yeah. So AB odd with A bar B bar. Very good. So you will record XNOR gate. But actually XNOR gate, yeah, 7486 is a commercially available XNOR gate. You check up if it is available commercially, you can make use of that. Okay, otherwise you have to make use of two and thank you. So XNOR gate basically, if you want to realize it, it will be via some AND or arrangement. Okay. Anyway, but in principle you are right. So you can use a XNOR gate, equivalence gate between up and Q0. Thank you. Very, very good. But here what will be the case? Here, I think here will be XOR, no? AB bar plus, yeah, AB bar. So here you will have to use the XOR gate, here you have to use the XNOR gate. Very good. Thank you. Achha. So that means the design principle, I believe it is clear, no? So instead of modulo 3, you are asked to do, say, in the exam, in the class test, say modulo 5, you can do it. Clear? No doubt. Achha. Let me now proceed to the next topic. That is what? So far, any doubt? Okay. Now, we are now encountering what is called, it is a ring counter. Now, why the name is given like that? In this counter, the flip-flops are coupled as in a shift register. Now, this configuration is called end around carry shift register. That means this is the end of the shift register. You see, it is just behaving like a 4-bit shift register. Achha, normally, if you remember, once we commented like a shift register can be modified to act like the counter. See, shift register is an array of flip-flops, counter is also an array of flip-flops. The difference is that counter, if it's given as the clock input signal, so the number of pulses will be counted. Okay. And so for a counter, always you have got a specified set of states. For all the shift register, it may not be given. Okay, but actually, anyway, you are going to make the circuit behave like a finite state machine. That you remember. So definitely, we will have some what you call set of, sequence of states that will be specified. So if you have to design a sequential circuit, you need a state sequence, and accordingly, you have to design the binary excitation table, and from that, find out the connection. Sorry, find out the mechanism by which the different excitation inputs of the flip-flops can be driven. Okay, that's all. Now in this ring counter, you see that as if the area of flip-flops is connected in a ring, because the last flip-flop output is fed back to the input of the leftmost flip-flop. Last means the rightmost flip-flop. Okay, its output is fed back to the input of the leftmost flip-flop, and the clock is being driven synchronously to all the clock inputs. So what sort of counter do you get? Why we call it a ring counter? Suppose the ring has got 4 one. So here one places the leftmost flip-flop in the set state while the all others are in the reset state. So that means this is in high state, the others are in 0 state. How we can do that? The question. See, now that you have got a knowledge about the presence of asynchronous state and clear, definitely you can make use of that. So I just incite your curiosity, and I'll tell you in practice what we do. We put a small RC circuit. Okay, this is the simple connection. The resistance, the other end is kept to +5 volt. And between R and C, this junction point is connected to different asynchronous points. The capacitance other end is grounded. So when you switch on the circuit, in all probability, the capacitance will remain discharged. Okay, and then it will charge up via the RC time constant, 0.7 times RC. Okay, so what will happen if you feed this to the preset input of FF1 and the clear input of FF2, FF4, then as soon as you switch on the circuit, this initial state will be accessed. Okay, so the ring counter, it will go to this initial state. Is it clear? How do you get? I have just given you a small suggestion. Okay. Now, what will happen? This this set state will advance from flip-flop to flip-flop with the progress of the clock pulses. Okay. So I have not drawn the waveform diagram. It is very clear. So this one will progress from left to right. And you see this 0 will come here because this 0 is connected. So next it will be 0, 1, 0, 0. Then again in a diagonal fashion, the 1 is going from FF1 to FF2, then FF3, then FF4. And finally, again this 1 followed by 3 zeros will be accessed after a period of 4 clocks periods. So it is a modulo 4 counter. Clear? Why it is called a modulo 4 counter? Because only 4 distinct states are there. Although we have got a 4 flip-flop, but no less than 2 to the power 4 of 16 states are possible. Only you have got only using 4 out of the 16. So 12 states are unused. We can say this is a huge wastage. Yeah, I agree. But you know what is the advantage? Advantage is that you do not require any separate decoding logic. Okay, that's what. Advantage of the ring counter is that no decoder is required, since the state of the counter is read by noting which flip-flop is set. So that means you can put an LED here, put an LED here, so 4 LEDs if you put, okay, right? So if you put 4 LEDs, say L1, L2, L3, L4, if a particular LED say L3 is glowing, I know that it is passing to 0010, or L4 is going 0001, or L2 0100, something like that. Okay, right? So reading of the ring counter is of huge ease, you can say, very easy. Advantage of that is the prime advantage of the ring counter. Okay, so no decoder is required. The decoding logic is absolutely simple. Instead of the counter is read by noting which flip-flop is set. Okay, another advantage is that as the counter is synchronous in operation. Synchronous means all the clock inputs are driven by the same system-wide clock and requires no gates external to flip-flop. The counter is very fast. Reading takes almost no time. Okay, so apart from the flip-flop, you see only wires are there, but no gates. So definitely with the paucity of combinational circuit elements, the operation of the circuit is very fast. But what is the disadvantage? Disadvantage is that if you extend this principle to get a modulo 16 counter, you require no less than 16 number of flip-flops. So it is very uneconomical of flip-flops. Thus, a modulo 16 ring counter will require 16 flip-flops, while a modulo 16 ripple counter will require only 4 flip-flops. Right? So economy in the number of flip-flops we can improve. How? The next counter we are studying. That is by going for a switch tail ring counter. So this is a normal ring counter. We are just now studying a modified version of this ring counter only to improve the economy in the number of flip-flops. So you see that we require too many flip-flops here, right? So if you want a modulo k ring counter, you will require k number of flip-flops, and k can be as high as 32, 64, something like that. Instead of that, if we now employ a switch tail ring counter, I will require only half the number of flip-flops. Okay, so a decade or modulo 10 switch tail ring counter requires only 5 flip-flops. Now, how the connections are done? Connections among the flip-flops are almost the same as in a normal ring counter. Only point of difference is that for the rightmost flip-flop, instead of feeding the the normal output from the rightmost flip-flop, we are feeding the complementary output of the rightmost flip-flop to the data input of the leftmost flip-flop. Okay, so only from the rightmost flip-flop, that is FF5 here, Q5 bar rather than Q5 gets connected to the data input D1 of FF1. Okay, now it has become customary to draw the circuit diagram with the switching at the end. That accounts for the name switch tail. N means as if this is the tail of the counter. Okay, the bottom one means the complementary output. We are calling this to be the tail of the counter. So at the end of the counter, as the switching is done at the tail, so it is account for the tail of the chain of flip-flops. This accounts for the name of the counter. So now you may be interested to see here the decoding logic of the switch tail ring counter will be somewhat involved, somewhat complex. In the simple ring counter, decoding is absolutely simple. No need of having some external logic. But for the switch tail ring counter, you will have a proper decoding logic, and also will identify that both the ring counter and the switch tail ring counter has got some problem because lot of states remain unused. So the problem of lockout will affect the operation of the ring counter as well as switch tail ring counter, and how to prevent that, how to remedy that. That will also learn now. So switch tail ring counter means that we have the number of flip-flops required to be half the modulus or the base of the counter. If you require say modulo 14 switch tail ring counter, I will require 7 number of flip-flops, right? That's why we are having 5 flip-flops and we can get a modulus of 10, value 10 by this connection. Now see. So these are the states of the switch tail ring counter that we have seen, this 5-bit switch tail ring counter. But see, the decoding of this counter will be a bit involved. 5 variables are there, okay, and these are the states. For your benefit, I am writing this. Suppose you start with all 0 state. Say you want to get the total sequence. So then what you will get? You will get Q1, Q3, Q4, 5, where Q1 is the state of the leftmost flip-flop, Q5 is the state of the rightmost flip-flop. So start with all 0, then 1 will come. Why? Because Q5 bar is connected. Just see. So 1, 0, 0. Then again Q5 bar is 1, so 1 will be coming here. Again Q5 bar is 1, so 1 will be coming here. Till you see that this state. When all the 1s are reached, then Q5 bar becomes 0. So now 0 will start coming. Again 0 will be padded up towards the left end till you get 0, 0, 0, 1. Again all 0 will come. So these are the all distinct states. No more states are possible. You count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so this is a modulo 10 counter. Okay, modulo 10 switch tail ring counter. Now, as far as the decoding logic is concerned, you see these are very interesting. You require only a two-input AND gate or a two-input NOR gate. And you see that 5 variables are there in all 2 to the power 5 or 32 states are possible, but you are using only 10. So 22 states remain unchanged. That's why when you have to work out the decoding logic, there will be 22 X's in the 5 variable condomer, and that is a huge benefit. That leads to lot of simplification. Okay, right? You can put on, right? So, and also I've written, say, what are the decimal equivalents? 0, 16, 24, 28, 10. Okay. Now, if you write it, you can just those which are not used. For example, 2 is not used. 2, 4, 5, 6, 8, 9. So all the 22 you connect with X. Now you want to decode, say, state 0. How will you get it? Yeah. So for the state 0, you put a 1. Okay. For the remaining 9 states, you put 0. Right? So 1 plus 9, 10 plus 22 unused. Now you combine. If you combine, you find that these 4 can be combined in the corner. So if you combine, if you can absorb 8 number of nearest neighbors, then you can remove the part 3 equal to 8. So 3 variables you can remove, only 2 will remain. And what are they? That also you can find. It is to be Q1 bar ANDed with Q5 bar. Okay, so Q1 bar ANDed with Q5 bar means it's a NOR gate. Q1 and Q5 are the inputs of two input NOR. Hey, don't talk, please. Okay, so decoding logic for counter state 0, I have got here as Q1 bar ANDed with Q5 bar. So complement of the flip-flop outputs, complementary outputs will be ANDed, right? So you will get a two input NOR gate. Similarly, in the exam, you may be asked to decode some other states like that. So you'll be able to do that. Okay, it's a very simple exercise. So work out the decoding logic like that. Now, what is the disadvantage of the ring counter? See, this is the state table of the decade or mod 10 switch tail ring counter. This is the way we can work out the decoding logic, right? By drawing a 5 variable Kundu map. But what is the disadvantage of the ring counter is that there are 22 unused states. So there is a good chance that if an unused state is reached somehow, the counter cannot come back to a new state. For example, suppose it reaches 1010, this particular counter. So it will be it will be hovering, it will be restricted to these 2 states only. Okay, so you will get a somehow if it falls into this unused state, and it will be cycling around only 2 unused states. So modulo 2 cycle of value 2. Okay, so you get it. Is it clear? So how to remedy that? The remedy, you can see, remedy will be that you have to make use of it. Hey, why are you talking? Who is this? I've been sending requests, no? Can you name yourself? Identify yourself. You can make your mic silent and you can talk. What is the problem in that? Okay, so you see that how we can set a remedy for this disadvantage is that how to prevent the lockout. To the prevention of lockout, you see, you require an AND gate. You connect, I mean, where exactly you have to set the connection. Okay, similarly, one thing let me tell you, you can do this small exercise. Here, the connection is made from the tail of the connection. But instead of Q5 bar, you could have also connected from Q4 bar to D1 or Q3 bar to D1. Then you see what are the states you'll get starting from all 0. Maybe the state assignment table will be somewhat different, but there also you will get a modulus 10 counter. That you please all do. Okay. So here I have done it. It is called switch tail ring counter because it is customary to make the connection at the tail of the counter. So Q5 bar, the complementary output is connected to D1. But instead of connecting Q5 bar, you could also connect from Q4 bar to D1 or Q3 bar to D1. Okay. Then also you will get a repetitive sequential circuits, right? Just work out that. Achha, so the disadvantage, as we have noted, is there is a lockout possibility. Okay, So lockout means if the system falls into one of the unused states, okay, so then it cannot come back to an used state. So this is the, you will get a subsequence you will be generating, a modulo 2 counter will get, but this is useless for the intended purpose. Okay, so you have to take into account, you have to take some mechanism such that this lockout can be prevented. And what is prescribed is that you have to put a 2 input AND gate. Okay, you just connect to external to complementary output. Now how this has come, okay, I do not know, but the remedy is provided like this. 2 input AND gate, you have to connect at the end. So instead of connecting only Q5 bar, now you put ANDing of Q4 bar and Q5 bar. You may try to find out why this works. You know what is the benefit? The benefit is that I've done also experimentally, that suppose some unused state the circuit falls into, it will definitely be able to come back from the unused state after going through some, possibly some more unused states. Once the prescribed, one of the prescribed state is attained, after that it will continue to behave like a. Also, one thing I have seen, you please see whether I am correct or not. If you connect Q4 bar and Q5 bar together, AND it and feed it to D1 instead of connecting only Q5 bar. So if you connect only Q5 bar, you will get a modulo 10 counter. However, if you feed the AND output of Q4 bar and Q5 bar and you connect it to D1, you will get the modulus not 10 but 9. Okay, provided if you start with all 0, you see that I am getting to these states, and I believe I am correct, but please you see if I am wrong or not. So I get a counter with the modulus or base to be 9, not 10. So start with all 0, since ANDing is involved, so 0 and 0, so 1 will be coming here because Q4 bar is 1, Q5 bar is 1, so 1 will be coming. So it will go till this point, right? So it will be all 1, then 1 will be coming here. Now from this point onward, you see that Q4 bar is 0, Q5 bar is 1. So hence after that 0 will start coming till it attains this state when both of them become 0. Right? So you see 1, 2, 3, 4, 5, 6. Oh, yeah. So no, this is a modulo 9 counter. 1, 2, 3, 4, 5, 6, 7, 8, 9. So it is a modulo 9 counter, is it not? Okay. I think I'm correct, but still you see, I am getting these 9 states, 9 distinct states. 1, 2, 3, 4, 5, 6, 7, 8, 9. Now, suppose the counter falls into an unused state. Say you take any unused state, say 0, 1, 0, 0, 0. So then it will cycle through this state till it comes to, say, suppose it falls to an unused state 0, 1, 0, 0. Then it passes to this till it comes to the all 0, which is one of the unused, one of the used states. So when it falls into the used state, then it will be able to recover from the error. So error recovery is possible only when the counter, even though it falls into an unused state, goes through some further unused states and then it gets back to one of the used states. Okay, is it clear? So this is about the switch tail ring counter. Any doubt so far? See, ring counter has also got its uses. It also finds use in the computer architecture. That means ring counter finds use as one of the controller element when we are studying about computer architecture, particularly as I have said, control unit and processing unit. So in the unit when you have to design, always it will have a counter at the heart of the design. Okay.
Sir,
Yes, please.
Initial.
Yeah.
Sir, you explain the initialization of the ring counter once again.
Okay. Yes. So this is a interesting. You see that we are missing your physical presence. So in the laboratory, you could have. I mean, even in your house also, if you have got arrangement, you can just start. If you have a breadboard, you can experiment this. Initialization, you see, it is possible to initialize the state of any sequential circuit to a desired state. Not always that it should be all 0, but it can be 1 ones also. Definitely know the position of flip-flops, okay, and the state of the counter, state of the sequential circuit. Then suppose here the it is 1 followed by 3 zeros. What we can do, you just employ a simple RC circuit. Okay, the value of the RC circuit should be chosen such that the RC time constant will be much less than the clock on time. That you can do. Okay, say choose these to be a value of 0.1 microfarad and so on, R to be some kilo, okay, 3.3 or 4.7, whatever. So based on that, you can find that some microsecond of clock period. So RC time constant should be much lower than the time period of the clock, because its effect should last for only few seconds or only for much less amount of time than the clock period. So if you switch on the circuit having made this connection, that means keeping a simple RC circuit and connecting the joint of the RNC to why I am connecting to preset of Q1 and clear input of the remaining 3, because I want that when the circuit comes on after switching, it should go to set state and the remaining flip-flops should go to reset state. I want this to be the initial states, because Q1 is nothing but the state of the FF1, Q2 that of FF2, Q3 that of FF3 and Q4 that of FF4. So if I want the initial state to be 1 followed by 3 zeros, this connection I'll make. Suppose I want something else, say 0001, then what I'll do? Then I'll connect this RC joint to clear input of FF1, FF2, FF3, whereas preset input of FF4. Then the initial state we'll find will be 0001. As I want it to be 1000, so that's why the common point I am connecting to the preset input of FF1, whereas clear input of FF2, FF3, FF4. Is it clear now? Then after, so this will persist only for some microsecond. After that, the control will go. So it will be under the control of normal clocking operation. Okay, so this happens just at the beginning. As soon as you switch on the circuit, and immediately normal operation will take over. Okay, because this capacitance will be charged up very quickly via this resistance. And how much time it will require? 0.7 times RC. If you take the value of EC to be very small, R to be very small, then it will, in no point of time, it will come up, the C will become high. And normally the asynchronous state and asynchronous clear inputs are active low. Okay, so moment the capacitance it becomes charged up, then its control is no longer required. Right? So only at the beginning of the operation of the circuit, it will be logic 0, and hence it will affect the asynchronous set and asynchronous reset of the other 3. So then the initial state will be 1 0 0 0. But after that it is normal operation. Is it clear now how to initialize the state of an encounter? In fact, not only the encounter, but any sequential circuit you can do it. Okay, because you know where are the flip-flops and what is the desired initial state. See, when you do the state assignment here, as if there are this is a 4-state sequential circuit, and we are assigning the states to be 1 0 0 0. And if you want it to be the initial state, then you make arrangement for this. This is called power on reset circuit. This simple RC combination is called a power on reset circuit. As soon as you switch on the power, okay, then this RC circuit will tend to affect the state of the flip-flops, but that too only instantaneously, that too for few instants right at the beginning of the circuit operation. After that, it will be the normal circuit operation under the governance of clock. Okay, that will go on. My dear friend, is it clear? You have got any doubt? Hello.
Yes, sir. Thank you.
Okay, thank you very much. Okay, right. So next, what we'll do, you know, we have been studying about counter. Now, a very interesting circuit we'll see. That is switch trailing counter. Also, I believe it is clear. Achha. Next, we take up the study of sequence generator. Now, as the name suggests, it will generate a sequence, and that sequence will be known to us, not arbitrary. Okay, so we are asked to generate a particular sequence by employing a shift register type of circuit. Okay, so it is nothing but a modified shift register, you can say. So a sequence generator is nothing but a sequential circuit, a synchronous sequential circuit, which generates in synchronism with a clock a prescribed sequence of bits. And shift registers can be adapted to behave like sequence generators. And what is the length of the sequence? Right, so length of the sequence means, see, it is a random sequence, you can say, or pseudo-random sequence, not absolutely random. Pseudo-random is that a sequence which has got a finite length. And you are reading the sequence, still the same sequence will be regenerated. So length of the sequence means you are reading the beats one after another till the beat pattern will repeat itself. The number of successive beats in the sequence before the beat pattern repeats. So I give one example. You see 3 1 followed by 0. I'm just repeating this. You can see 3 1 followed by 0, 3 1 followed by 0. So length of the sequence is obviously 4. But the number of ways you can read it will be plenty. You can read it say 3 1 followed by 0, or you can say 2 1 followed by 0 followed by 1. Okay, or 1 followed by 0 followed by 2 ones. So length 4 each time. Also 0 followed by 3 ones. So although it is a length of 4 bits, you can read it in 4 different ways. Okay, but now you can question. Basically 4 flip-flops are there and you are reading the state of the flip-flops, nothing else. But at the same time, the 4 ways you will get by reading the normal outputs of the flip-flops. There are 4 flip-flops. What about the complementary, what are the complementary outputs? So then you will get 4 more ways. That means the same sequence you can read in 8 different ways. All are same. So that means if you have a same circuit, you will be able to generate no less than 8 different sequences of length 4. Okay. Now, depending on the depending on the okay. Sorry. Okay. So now you see that what are the sequences we are reading depending on the starting point. So if you start from here 1 1 1 0. So the above sequence may be described as a repetition of the beat pattern 1 1 1 0 or 1 0 1 1 or 0 1 1 1 or 1 1 0 1. So these by reading at the normal output of the flip-flop. But now if you use the sequence available at the complementary output of the flip-flops, you see you can read it in 4 different ways. So you can read it, say, instead of reading 1 1 1 0, instead of reading 1 1 1 0, I can read 0 0 0 1. Instead of reading 1 0 1 1, I can read 0 1 0 0. That means I'm just reading the Q bar, not Q. So that means 8 different ways. Hence, a repetition of any one of the 8 patterns of length 4 bits will constitute the same sequence. Right? So, and just diagram, the basic structure of the sequence generator, my dear friend, will look like this. See, to generate a sequence of length S, minimum number of flip-flops required is N. Now, the theory, if you want, okay, that I'm not able to provide you because we are just reading about the digital circuits. The actual theory, if you want how it is possible, generate a sequence of length 4, then you require the knowledge of linear algebra and what you call different other aspects. So combinational theory also you require. So it is not possible for us to go there. We are just interested in circuit realization of the various sequences, and to find out we have to be satisfied with using the minimum number of flip-flops, but at some point of time we may fail. That means the prescribed minimum number of flip-flops may not do. Then we have to keep on increasing the number of flip-flops till we are able to realize a particular sequence generator. Let me describe that. So basically we want to generate a sequence of length S. Minimum number of flip-flops is N. So if say S becomes say 13, okay, so s plus 1, that means 14. 14 is less than or equal to 2 to the power n. So minimum value of n equal to 4. Okay, because 2 to the power 4 equal to 16. So to generate a sequence of length s, minimum number of flip-flops is n, where s is less than or equal to 2 to the power n plus 1. 2 to the power n minus 1. Now why this minus 1 is coming? That also I can give you a simple answer is that, you see, normally we leave out the sequence when all of the flip-flops are in reset state. See, here we are feeding back a function f. This f is a function of all the flip-flops outputs q1 to qn, and that we are feeding in d1. So it is like a modified shift register. That's why we have said at the very beginning that a simple shift register can be adapted to function like a sequence generator. So what is the problem for us? We'll be given a prescribed sequence. We have to work out a circuit which will be having the shape of a shift register. Only thing is that at the input of the D input of the leftmost flip-flop, we'll just feed a function of all the n variables. N variables means all the n flip-flops are there, their output will act like the Boolean variables. Okay, so that's what we are doing. And now if we put all the flip-flops are at reset state, yes, that state normally you will never find, because this circuit will involve invariably the presence of some XOR gate or something. So it is found that if all 0 states are there, then it will be, the next state will also be all 0. So then the system will be stuck. So it will not be able to function. That's why normally the all 0 states is prevented from coming into the state sequence, and that accounts for the occurrence of -1 here. So if you have to generate a sequence of length s, the minimum number of flip-flops should be taken as n. Then 2 to the power n. So although it will give rise to if you have say 4 flip-flops, although it will give rise to a sequence of length 16, but leaving out the all 0 state, I'll get the maximum length sequence. The length of the maximum length sequence will be 15, not 16. Okay, and also I'm showing a brief. See, as it is a repetitive, say pseudo-random means what? That bit pattern will repeat. Absolutely random means it will never repeat. Pseudo-random means the sequence will have a finite length. So that same sequence will keep on repeating itself from time to time. So then it will, just like if you draw the state transition diagram, you will have a cycle that starting from the initial state, say S1, you go to S2, then S3 and so on till you get SP, then again fall back to S1. So that means it is a cycle of length P. And let me assert that here none of the P states should recur in the cycle. Why? Because suppose S1 recurs, that's what I have written in a a faded way. So if S1 requires and S2 is designed to be the next state for S1. So once S1 recurs, it means that a subsequence will be hence generated. Right? We are looking for the sequence S1, and the presence of any state, any given state, will determine the generation of a unique sequence, my dear friend. Okay, so if it is of the length say P, then it will generate a sequence of length P. Okay, so but if accidentally some of the states come here while we are generating the state sequence, then what will happen? You know, once S1 comes back, then it will be a subsequence. A lower length sequence will be generated, but that we do not want. We do not want in subsequence, but the entire sequence, right? So it is mandatory that if you find while trying to design the circuit, if some state occurs more than once, then we have to keep on increasing the number of flip-flops, right? Why we say? Because increasing the number of flip-flops only you can increase the length of sequence. So we do not want a subsequence. So then increase the length of the sequence, and hence we get finally the desired state, desired sequence. Clear? Let me try out with some examples. Read the problem. Read the problem. So what you are supposed to do here? So you see, here we are asked to generate a sequence of length. What is the length? You can read. It is length 15. 1 followed by 30, 4 plus 3, 7, 7 plus 3, 10, 10 plus 2, 12, 12 plus 3, 15. So a sequence of length 15 we are supposed to generate here. So record minimum number of flip-flops is 4. Why 4? S is less than equal to 2 to the power n minus 1. S equal to 15, so 15 plus 1, 16 to the power n greater than equal to 16. That means n minimum number of 4. Mind you, n is the minimum number of flip-flops. We may succeed with 4. If we do not succeed with 4, when we do not succeed with 4, when any state will recur in the state sequence table. This is the state sequence table. Earlier, we were calling it to be state assignment table, but now we call it to be state sequence because the sequence is given. So we are bound to work as per the dictated sequence, right? Now look at how the system will look like. It will consist of n flip-flops. So that sequence of length 15 will generate here in time. The same sequence will generate here in time because it is nothing but a ring type of circuit only for the disconnection. That means it is an array of flip-flops, and whatever sequence I get here, the particular sequence will repeat only after delay of 1. So after a delay of n minus 1 clock cycles, the same sequence that is available here will repeat here. Clear? Right? And whatever be the sequence of at D1, that will repeat at Q1 after 1 delay. So Q1 at T plus 1 will be D1 at T. Okay. Q2 at T plus 1 will be Q1 at T. And Qn at T plus n minus 1 will be Q1 at T. Simple equation. Okay. Right. So what we do first, let us write out the sequence. So Q1 means the Q input of the leftmost flip-flop. Q2 is its immediate right neighbor. And as we have 4 as the starting plan, as we have got 4 flip-flops, so FA4 is the rightmost flip-flop. Okay. So like that, this is the sequence for 15 states. Then the same sequence will generate here after delay of 1. So you just diagonally put this value. So once you fill up the Q1 column, next you fill up Q2 column, but you start from 1 point down. Okay. And similarly Q3 you write 1 column down. So from here, third, fourth, and finally Q4 from the 4th row onwards. Then the question, how will you fill up this vacant state? Okay. That we will fill up in order to facilitate you to fill up. That's why we have extended it to 3 more clock cycles. Okay, so 100 up to 1. Again, the same sequence will repeat. So I write only for 3 clock periods. You know why? Because this will be repeated here. When you are writing this, so diagonally you see that this triangular matrix, this 3, 1 and this 3, this triangle we cannot generate at the very first go because I write this one, after delay I write this one, for the Q3 I write after a delay this one, and for Q4 I just write, okay, right there. But what about this triangle? This triangle is 1, 2, 3, these 6 elements. These 6 elements I can fill up. In order to enable me to fill up this, that's why I've extended beyond 15. Okay, so once you write, I can write this and then I can diagonally float this. Okay, so I can fill it up clearly. So then these 6 elements, 1, 1, 1, here it happens to be all 1, but not always. So these 6 will I just repeat it here. I'll echo it here. Okay, I'll just replicate it, right? And how do I fill up? This is the function of the combinational circuit. What I have to design, basically the problem boils down to designing of a combinational circuit by n variable combinational circuit, nothing else. So I have to fill up this. So how do I fill up? So you see that now I look at the Q1 column. So this 0 would have come from D1. So it is now the reverse way. This will go up diagonally. This 0 will go up, 0 go up, 0 go up. And finally this 1 will go up here. So I can fill up entirely the 16 values for the D1 input. I have written for you. Note all the D1 column entries are filled by inspection of the Q1 column. So my dear friend, I believe you know how I am filling up the entire table. You know, for Q1 I can get it directly from the specified sequence. Q2 I just write it here, only repeat it, and the 15 elements I can write. 14 elements. Then this one I will come here. Okay. Then for this 3 I can write from here. So 13 elements. These 2 will come in the top. And finally for Q4 I can write this 12. the next 3, it will come over here. So then all the 4 columns get filled up, and now as far as the filling of this output column D1, you just look at Q1, just rotate, flip it towards the diagonal. This 0 comes here, then this 0 goes here, right? This 1 goes here, and how we'll fill up this one? That will come from here. Okay. So all the D1 column entries are filled up by inspecting the Q1 column, the leftmost column. Clear? Now, we have to, before we start up the design, because before we draw the 4 variable Kundu map, we have to be careful. We have to see any of the 15 states have repeated here. If it repeats, then you have to increase the number of flip-flops from 4 to 5. So how? When you construct a sequencing table as shown in the left, we must ensure that during generation of the complete sequence, no state should be repeated. Okay. For a present state, uniquely determines the future development of the sequence. Okay. Based on the unit state, that's why I have drawn this circuit. So if we start the sequence from here, I'll get a particular value. If I start from S2, I'll get another sequence. Maybe of the length sequence. Maybe the length of the sequences will be same, but the way I am writing the sequences will be different. That's why we have shown that a sequence of length 4 can be written in 8 different ways, at least in 4 different ways. So for a present state, uniquely determines the future development of the sequence. So if a state repeats itself, it will imply a recurrence of the succeeding sequence. Okay, it will imply a recurrence of the succeeding sequence. Right? So that we do not want. In the table, every possible state occurs just once. Here, however, I see 1, 1, 1, 1, it has not occurred. 0, 1, 1, 1, it has not occurred. 0, 0, 1, 1. So as you can check that if you leave out all 0 states, apart from that, all 15 states have occurred. So in the table, I find that except for the all 0 state, all states have occurred. All 15 states. This all 0 state must be excluded. For in this state, D1 equal to 0. Okay. And so the next state will also be 0. That becomes useless. Here what we do next, as we are sure that there is no anomaly, that means all states are unique, all the 15 states are unique, have only occurred once in the entire state sequence, it is of length 15. That means in the state transition diagram, we have a cycle of 15 states. Now if we draw a Kundu map of 4 variables Q1, Q2, Q3, Q4, I get that by combining second and fourth column, I'll get this D1 to be the exclusive OR of Q3 and Q4. Clear? Okay, Q3 and Q4. So the circuit is very simple. So here, however, the problem is simple. Problem is not the problem is simple. We are lucky enough that here all the 15 states are unique, but not always will be that much fortunate. But at that time, what we have to do, we have to keep on increasing the number of flip-flops till all the states become unique. How? I think this problem is clear, any doubt? So given any sequence, you are asked to design a generator, you will take up this mechanism. Okay. So here you see that this function, this feedback function is as simple as an XOR gate. Most of the times you will be asked to use using only XOR gate. Okay. Now, next problem. So here, suppose you have to generate a sequence of length 7, 1, 0, 1. So 2, 3, 4, 5, 6, 7. That means you require S is less than equal to the power n minus 1. So S plus 1, 7 plus 1 less than equal to the power n. So minimum value of n equal to 3. Mind you, minimum. Not that you will be succeeding. So here if you write it, you see in Q1 this is occurring, then in Q2 this will occurring, and that 0 will come here. Then here also it will come 1, 0, 0. Then you will get the other 1, 0 you can fill up by looking at this. So this 1, 0 will repeat here. Okay, so it will just flip in a diagonally up. Here it will come diagonally down from right to left as you are going. And here when you have to fill up the unfilled entries, you have to take the value from your left neighbor, but in a diagonally. And now it will proceed diagonally up. Okay, so like this. Okay, so you can fill it up. And then D1 to 0, again it will go diagonally up, 0, 0, up to 0, 0, and this one will come from here. Okay, right, so you can fill up the column. But now you see at k equal to 1, the clock interval k equal to 1, k equal to 3, same states repeat. 101 is repeated. Also, D1 is asked to be 0 here, D1 is to 1. That means this is also not feasible in the sequential circuit design, that for the same state you are asked to design two different output values. That is not possible. Okay, because D1 is like a output of a combinational circuit. So for the same state, we cannot design different values of output. So D1 should be a fixed function of the state. Is the two different values of D1 are not permitted for the same state. Similarly, for k equal to 5 and 6 also, if we 111 recurs, but with different values of D1 being implied, that is also not possible. So what we do, we understand that now we are not fortunate to develop our circuit using only 3 flip-flops to increase the number of flip-flops. Okay. So we have to try to solve the problem by increasing the number of flip-flops until each state in the state is unique. So go from 3 to 4. That means we rewrite this, fill this first column, fill the second column, fill the third column, and fill the fourth column. And now if you write, you find that in all 2 to the power 4 16 states are possible, but you are only using 7 of them. That means 9 states are unused. And also in the state sequence table, you see that all of them are unique. It is not recurring. 1011 only once. 0101 only once. 1010 only once. 1101 only once. 1110 only once. All ones are 1, 0111. So these are not recurring. Okay. So that means we now succeed. We can design the circuit. We find that here I require a 3-input NAND gate. Okay. Right. So you can combine by making use of the 9 unused states. So many unused states are there. You see 1, 2, 3, 4, 5. This 4, this 3, then XX. So 9 states are unused. You can get it by, it's a NAND combination of so NAND combination, that means a 3-input NAND gate will do. In the present problem, by introducing a single additional flip-flop, each state in the state becomes unique, and you can design the circuit. Okay, so you can also verify the operation of the circuit. So if this 1011 is the initial state, then what will be the next state? You can easily verify. Okay, so that concludes the discussion on the topic of counters and sequence generators. So far you have got any question? Hello, are you present?
Sir, in the previous diagram of the ring oscillator, like there was a connection missing, I thought.
Which one? This one? Is it this one? This is
So there, no, sir, not this one. A previous one in a previous page.
Okay, let me take you to that. Yeah. This is actually not a ring generator. This is actually.
So it was drawn in brown.
Sequence generator. Yeah, these are also sequence generator. Let me see. Not this one, I believe. Okay, let me take you. This one, no. This is the diagram of a switch tail ring counter. You say it is drawn in brown. Here, I believe here. Oh yeah, yeah, you're right. This is missing. Thank you. Yeah. So this is missing. Correct. Please make all the corrections. Switch tail ring counter. This should be connected. Q2 and D3 are connected. Thank you. Anyone else? Okay. So let me recapitulate then what you have learned today. So you have learned about a decade counter using direct input. That means a non-binary counter you are designing, but using the very simple and straightforward way of drawing the ripple connection. So asynchronous binary counter, if you are asked, you can do it without thinking at all, and that too in a forward direction, is it not? And then you just slightly modify it to get a non-binary counter, but the modulus should be less than the value of the 2 to the power n, where you are using 2 to the power n flip-flops. Sorry, where you are using n flip-flop. Is it correct? Okay, so straightforwardly you pick up draw the circuit required for the ripple counter that will give you a modulo 2 to the power n counter. And suppose you have to draw a modulo k counter where k is less than 2 to the power n, you can easily design it by using asynchronous set and asynchronous reset input. Okay. So here you are choosing to do it using asynchronous set input. How I think this is clear, fair enough, simple enough. Okay. So use an AND gate where the inputs are coming from the clock input and those flip-flop outputs which are in set state in the pre-final count, and then the output of the NAND gate will go to the set inputs of the flip-flops which are in reset state. But know for sure that the thing is normally S and R will always be direct set input, the asynchronous set input will always be active low. So you need not worry about that. Next we study about up-down ripple counter. Ripple counter is very simple, just toggle between the complementary and the normal output. But when you are asked to design a non-binary up-down counter synchronous that too, then you have to design a bit. That means work out the state, the requirement of the excitation inputs for the forward direction and that for the negative direction. But here a word of caution, let me tell you. Here, whatever states you are giving, or you are designing for, see, this is why I am telling you again, because this is your choice only. So you may decide to use 000110, but your friend may decide to use 001110. Okay. Or your another friend can decide for any. So there are four choices. Ask you. Okay. So here, you have to take. There are four combinations. Okay, and you can take whatever way. So remember that for up counting you require three states. The same three states will be recurring, but in the reverse direction. Do not by mistake, let me tell you a word of caution. 000110 if you are taking, do not by mistake take the counter in the reverse counter, say 11. 11 should not come there. Are you getting it? Say if you take 0001 and 10 in the forward direction, you should have the same states only. Do not include one by mistake in the reverse direction. These same three states will be there. Okay, dear friends, do you get it? The problem will be more critical when you are taking some modulo 5. Modulo 5 means you are leaving out 3. So whichever 5 states you take up for up counting, the same 5 states should be there for down counting. Do not by mistake take any state which belongs to down counting, not up counting, or some state which belongs to up counting, not down counting. The same states whichever are involved in the forward counting, that should be involved in the backward counting. Clear? Do not make this mistake. And after designing that, the excitation functions will be there. So that means if you have two flip-flop J0, the 4 excitation function for modulo 5, modulo 7, you will require 6 excitation functions. So you have to carefully make use of J0, J1, J2, K0, K1, K2. Okay, clear? Next, what we studied about ring counter. Ring counter is actually a variation of shift register. Only the end around carry combination is there, this connection, and you can read it carefully. Read it very easily, and then switch tail ring counter to have better economy of the flip-flop, number of flip-flops, and then the decoding logic of the switch tail ring counter. And the danger that always is there for ring counter and switch tail ring counter is that if the system falls into an unused state, it will go from one unused state to another unused state and will never be able to come back. Okay, because it will fall into a loop. Okay, that loop is a vicious loop. So what you have to do, you have to make arrangements such that if it falls into the loop, the arrangement should be such that if it falls into some unused state, after going through a number of unused states, it should fall back to a used state. It can come there directly or by going via some unused states. So I have seen by experiment that if you make this connection, this will give you a modulo 9 counter, however, not modulo 10 counter. Okay, but the counter, if it falls into an unused state, then it will go through a number of unused states, then it will get back to a used state. So eventually a used state will be reached and then the counter will be able to operate. This is called error recovery. That means some fault has taken place, some error has taken place, but you can come out of the error, you can recover from the error. Okay, so if you make use of a simple AND gate, you can definitely recover from the error. Okay, is it clear? And finally, what you have studied about the sequence generator, that means you are asked to design a particular sequence. This is nothing but a modified shift register type of configuration. Okay, so you have to write the state sequence table carefully and see that no state repeats in the state sequence table. Okay, and if it repeats, then increase the number of flip-flops till you get all unit states in the state sequence. Here, for the first example, we are lucky that all the 15 states are unique. None of them will occur again in the state sequence table. So you can straightforwardly design it by drawing the 4-variable Carnot map and what is the excitation function. D1 is a function of Q1, Q2, Q3, Q4. Yeah. So you draw the circuit diagram. That's how we complete the design. But in the second example, although it is a sequence of length 7 and you require at least 3 flip-flops. So if I find that here at 2 occasions 2 states recur, 1, 0, 1 will recur at k equal to 1, k equal to 3, k equal to 5, k equal to 3, all ones recur. So then this is that means we are unable to design using 3 flip-flops. Increase the number of flip-flops from 3 to 4. Then I find that all the 7 states are distinct. Okay, so I have to draw a 4-variable Carnot map and solve for D1. I find that 9 states are unused. Fill them up with don't care increase excess, design it, get it. Okay, that's all. Anything not clear so far? You can put questions. So remember, dear friend, we'll have the class test on. Yeah.
Sir,
Yes,
the sequence generator, we are reading it serially, right?
Yeah. That means the same sequence you see will appear here. The sequence will appear here and the same sequence will appear here, but after a delay of time, 1 clock cycle. Same sequence after a delay of 1 clock cycle with respect to 2, after delay of 2 clock cycles with respect to this FF1. And similarly, Q4 will also repeat the same sequence, but after delay of 1 clock cycle with respect to FF3, after delay of 2 clock cycles with respect to FF2, and after a delay of 3 clock cycles with respect to FF1. That's all. It will be read sequentially. Yeah, you are correct. It is a synchronous sequential circuit. Okay, all the clock inputs of the 4 flip-flops are driven by the same system-wide clock. And this is a simple shift register, but for this feedback function. This feedback function, in general, it is a function of all the flip-flop outputs. Okay, so if there are n flip-flops, it is a n variable Boolean function. That you have to design carefully. Okay, you got it?
Yes, sir. So the sequence they mentioned, we would be reading it from Q4 only, right? Means unless it is mentioned otherwise in the question.
Oh yes, actually, all the flip-flop outputs will be accessible to you. Don't worry.
Okay. Okay.
All the flip-flop, yeah. So you can generate at any point of time. Actually, if you read it, say, let me tell you, if you read it 1 0 followed by 4 1 0, or if you read it 0 followed by 4 then 0 1, or you read 1 followed by 3 1 0 and like, so you can read it in different ways. A 7 length sequence you can read in 7 different ways. Clear? Say 1 followed by this, 0 followed by this, 1 followed by this. So I mean you will have 7 different ways of reading the sequence. The same sequence will be read. So and also starting from 1, this will also read, you will be able to read at Q1, Q2, Q3, Q4. But after delay of 1 clock cycle, after delay of 2 clock cycles, like that. Okay, so shift register you can say, yeah, so it is a period of 7 in this case. It is a sequence of length 7. Period is actually pseudo-random sequence. So actually you will have a class test on last day, that means 19. It's a simple syllabus will be there, so don't worry. I mean, yeah, so any doubt so far, you can ask question. Okay, if not, then we'll then meet again on Thursday, 8 o'clock, right? So any doubt so far? All of you are fine, doing well. Any doubt you can let me know.
Sir, could you repeat the date of the class test?
That is on next Thursday, that means 19th. Actually, institute says that by 20th we have to end all the classes, class test, sessional test. So that's what I'm keeping this on 19. Okay, because 21st I don't want to delay because because as we are instructed by the institute.
Sir, what are
Sir,
the
can we get to know our previous class test marks?
That is being checked. Sorry, that is being checked. That is being checked. Don't worry.
Sir, what are the timings of the next class test on Thursday?
Timing. Timing will be same as the class timing because we cannot go beyond the class timing. So it will be 8 to 9, like something like that. Well, on Thursday, yes, yes. On 19th. Because you have to attend the other classes also. That's what. I mean, we are asked not to overlap into the other classes. That's why we have to be strict. Don't worry. I mean, it will be from whatever we are studying in the class only. Nothing unseen you will get. So if you follow the class, I'm sure that you will not, but do well. You have to do well. So please, in your class notes, you have got anything doubtful, just let me know. Okay. One question was asked from somebody.
This is regarding the last class test.
Yeah, Nivedita. Yes. Hello. Yes, Nivedita.
Actually, yes, sir. The last class test question paper was quite lengthy for an hour. So, like, we kindly request you to just check with the length of the paper so it is doable within an hour.
Actually, the thing is that I was advised to do it, several factors are there. I mean, had you physically been present here, it would be not like that. So there, I mean, that is just a way of, I mean, don't get me wrong, don't misunderstand me. We cannot keep an eye on what people are doing. I believe all of you, but still, I mean, also to have a competitive flavor. I mean, you see, not that you have to finish 100%. I mean, so it is finally it will be relatively, that you will be relatively graded. So you have to maintain all the what you call the discipline and give your best. And even if you fail to answer all, doesn't matter. So finally you'll be graded as per the best of your ability, and also it will be relatively graded. So I mean, if someone of you finishes 100%, then I mean relatively you have to grade. No, that is the rule of the present competitive world. What you can say. But let me tell you frankly that if you give effort, you'll be able to, you'll be able to do very well in all exams. So my best wishes will be there. Now regarding that, regarding the length of the paper, I was advised, I don't say who, but in general, we have a class, among the colleagues also we discuss that. So it is a general things. Don't worry much about that. Yeah. Any next question?
Sir, I have a class.
Oh, yes. Okay, Snigdho. Okay, all the best. So then we'll meet day after tomorrow at 8 o'clock, and hope all of you are doing fine. Keep watch on your health, and also keep watch on the health of your parents, your friends, your neighbors, everybody. So wishing all of you a very fantastic Diwali. Anyway, we'll meet on Thursday also, and tomorrow also we'll meet for the lab. So wish you all a very happy future. Don't worry. I wish you all the best. Is still any doubt is there? You can ask me, those who are present, or you can send
Yes,
me.
sir. It was kind of hard to concentrate on the exam because the TAs were constantly calling our names. Like all of the videos are not visible because of bandwidth issues.
I know.
So
This time it will not happen. Yeah, Snigdho, I'll sort. Don't worry. I'll take care. I'll take care.
thank you, sir.
Don't worry. So that's why, some of you have written mails also. Yeah, so you'll be able to fully concentrate. Thank you very much. Any more doubt? Just, I want to see your smile. Please be happy. Okay. Please be in good health. All the best. Thank you. So I think you have to say goodbye now because you have got class now, no? All of you. Okay. Thank you very much. Hey, I have not taken your classmate. Yeah, sorry. Anyway, don't worry. Let me see. I have not taken your. I'm not very good at. Yeah. So attendance is there, right? Fine. Okay. So goodbye, all of you. Say something.
Thank you, sir.
Oh, thank you.
Thank you, sir.
Thank you, all of you. Stay fine.
Thank you, sir.